Can people hear what I'm saying?
Loud and clear.
Okay, excellent. Thank you so much. Okay, I suggest we get started. So before I go to the main part, I just wanted to at least show everyone some of the administrative things, and in particular where you can find the recordings of the lectures. So for those who haven't fully explored the Blackboard website, this is what you ought to be seeing in your student mode. And in particular, I just wanted to point out that there's a link here for Zoom. Click on it, you actually can go in here and you can see the actual meeting details. But also you can take a look at cloud recordings. And you can see here indeed topic is the digital classroom and the timestamp. And if you click on it, you can see recording and the audio as well. Okay, so that's number one. And I also like to go back this part here and show you that if you go to the course content, and I will also upload the slides. So this is an example where you can see the written notes, the written slides that that I've made, and these are also available for you, especially if you want to just as a PDF download these. I want to stress that these are really just notes that we've taken during the lecture, but that in time I will also release lecture notes that are more fully written and can be used as reference. Again, these are all available to enhance your learning. Okay. I also noticed so far I haven't seen anything on the notice board. So again, I'd just like to encourage people, for those who are interested, asking questions and so on, to post them here just for everyone's benefit. Okay, so that we don't have to ask the same questions over and over again. And finally, one last thing is that in terms of the exercise classes, I know that there are officially 3 exercise classes, and there's actually a poll going up. Let's see, it is outline. So indeed, exercise classes. How do you want to arrange your exercise classes? For those who haven't filled it in, please do submit your preference so that we know how to best deal with the exercise classes and see how your own preference for this. Now, I also know that formally, like regardless how we're going to do this, exercise classes when all the teaching is online, I also realized that there are still physical or virtual slots you need to fill in, and in terms of which exercise classes you're taking. And I just want to stress that if this is causing you trouble, right? If it causes time clashes with other courses that you do want to register, I personally don't mind particularly. Just get in touch with me, and I can work with the general office to get you in the right exercise classes, at least formally or kind of virtually, so that you can so there's no time clash. The expectation is that all of the material, even that we do in the exercise classes, will be made available online. I think that's also one of the advantages of doing things online, is that we can now, I can make these things available, and you can really take your own time to do your learning at your own pace, but also at your own time. I don't mind necessarily. Just let me know if you are getting into trouble with this, and I can make arrangements. Okay, that's pretty much it for the kind of announcements and kind of the administrative stuff. Are there any questions at this point, especially about maybe the website, like Blackboard, about the recordings or anything? I'll just give you a quick second to see any questions about it. Okay, feel free to either speak up, write it in the chat, or again, post it on the discussion board. That's a little bit up to you. But I don't see anything here, so I on with the main lesson. Just one last thing. Again, it's a little, online teaching is a little weird. It's a little impersonal. I do think that, I do encourage those who are comfortable with it, you're more than welcome to also open your webcam, just so that at least kind of people have the sense that there's a physical person. It also helps me to at least see some of your faces so that I know, who you are, and also that, whether you are enjoying the class or not. I also don't just stare at a screen and just talk and I have no idea whether people are actually hearing me or whether anyone's actually still here. Okay, so in that case, without further ado, let's just get started. I see some people indeed opening up the cameras. Appreciate that a lot. It's good to see everyone's faces, and makes teaching a little bit more personal. Okay, good. Let's get started. I hope that people enjoyed the last class. I know we went very slow, and that's just kind of to make sure that the course is covering everything to the fullest. But my promise is that we are going to pick up pace. In fact, at some point you may think the opposite, like, can we slow down a little? So just bear with me. These are things that we have to go through. But today we're going to take a look at a little bit more, I think what you may call physics. For me, maths is also part of physics, but we're gonna take a little bit of a look in different fields. Okay, so but nevertheless, before I do so, I do like to start every lesson with just recapping what we've done. So let me share my screen here and see. Okay, excellent. A little bit cut off too. Oh, this is perfect. Here. And I can write on this thing. Okay, let's basically just start with a quick recap. In particular, last time we looked at a lot of. This will have a very particular preference for different color. Otherwise, I like blue. Okay, so just as a quick recap, we are going to work a lot with vectors. That's why this time around I want to really start with just outlining all of the basics of vectors. And so in principle, what we do is we deal with vectors, and especially in 3-dimensional, in 3D vectors, we can typically write them as, for example, A equals, and then as a decomposition of 3 vectors, any 3 vectors. Okay, I can't stress this enough. Any 3 vectors can be used to decompose a general vector. Of course, they have to be 3 distinct vectors. You can't say E2 equals E1, then that doesn't work. But for any 3 distinct vectors, I can use them as so-called bases. And then these A1, A2, A3 are simply scalars, and there are components of this vector A, but in the bases A1, A2, A3. That's a basic representation of a vector, and in particular, very often what we do is we use the Cartesian coordinate system. So that's AX, EX, plus AY, EY, plus AZ, EZ. And these are the basic, rectangular systems. We've got X, Y, and Z. And this is very not be something very new. This should be something that everyone knows. And then we basically looked at very simple operations that we should all know. So we've got, for example, vector addition. Vector addition. If I do A plus B, then it's simply just all the different components. So I've got AX plus BX. X direction, and then AY plus BY in the Y direction, and I've got AZ plus BZ in the direction. Okay. Similarly, if I can multiply by scalar, by a scalar, so for example, 3A is simply just 3AX EX. Okay. Each component just gets elongated by this multiple. 3AZ EZ. Okay, so these are rather simple operations, but we also have operations where we have a vector with a vector. And so the first one is a scalar product. Scalar product. And here what we do is basically we've got A, B equals the norm of A, the norm of B, cosine theta. Or if you want to decompose it, it's simply AX, BX plus AY, BY plus AZ, BZ. Okay. And finally, we also have what we call the vector product here. So we've also got a vector product. This is a little bit more cumbersome, where when we have A times B, we actually end up with something that is by itself a vector as well. And in a compact form, we can write them this way. Just a norm. And this here by itself is simply given by EX, EY, EZ, AX, AY, EZ, BX, BY, BZ, and the determinant of this. Okay, so these are all the operations, the very basic operations that we want to do with vectors. And then, of course, they have their properties, so whether they commute, whether they're associative, whether they're distributive. And these are things that hopefully you should, at least if you don't remember them anymore, make sure you look them back up in mathematical methods. And then finally, we also have things like triple products. Triple products that includes A dot B times C, stuff like that. But we also have, for example, this scalar triple product, and then we also have a vector triple product, which is A cross B cross C. And they all have their associated expressions here. Okay, so this is just a very short recap of what we did last time around, where we just looked at vectors. And as we go along with this, we end up having to do a little bit more complex things. For example, take derivatives of vectors and vector fields. And that's really what we're working towards. We probably won't get to it this time around, but next time we will be looking at derivatives of vectors as well. This. So last time around, I also talked about the distinction between really more of the Newtonian or Newtonian experimental way of looking at physical laws. And in particular, the Newtonian dynamics is very much centered around this notion of forces. Okay? You have a force, and then something moves. So that's where Newton's three laws are related to. And that is one, of course, is the notion of inertia. If you don't apply any external force, the object is just going to go at a constant velocity. The second one is how the force is actually constructed as a rate of change of momentum. So this is just mass times the acceleration. And then the third one is just an action-reaction. But within these three laws, we have to bear in mind that this is always, the focus is always on a force. There's a force, and then something happens, something changes as a result of this force. But as we'll see in a lot of physical situations, this constant thinking in terms of forces may not be ultimately what is useful. The reason, or one of the reasons why, is because you always need something else. Right? You're not describing kind of the physical situation. You always need something else. You always need something that then reacts to something else. And that's why there's actually, or there was more of a push to think things in terms of physics. Like what is going on in terms of physics, and then, okay, what happens then in reaction to. So I think one of the places where everyone will have seen the notion of fields is actually in gravity. In gravity. Let's take a look at the concept of fields, but in this case in gravity. So gravity is something that we should all be very familiar with in terms of kind of even the basic physics behind it. So let's say we have a mass. Okay, so we have a mass. There, mass m, okay, and I'm just going to put mass m here. Okay. So now, one thing that I could do is I can ask, okay, well, what is the force on another mass? Okay, so now I'm going to have another mass, and I'm going to denote this by small m. So imagine I've got a mass with small m. And I know that there's a gravity force that then pulls this thing towards each other. But let's imagine I'm now putting another source here. This is another m. Now, with respect to the one in blue, what happens to what's the force of the one in green? Well, we know that, well, we expect that the force is going to be smaller. It's at the farther distance. So here, I would write, instinctively, I would maybe draw a smaller arrow. This is a smaller force. Now also, one thing they should note, that it actually points always to this big M here. And the attractive force is always in big M. Oh, by the way, when I draw this green one, I assume that the blue one, the smaller one here, does not exist. So I can now place M's everywhere. I could imagine an M here, and I get an arrow here, and I can place an M here, and I can imagine an arrow going this way. So wherever I put a mass, I can always associate an arrow. In this case, oops, did I draw? Oops, okay. I drew it not. Okay, let's just actually put it in the right place. So wherever I put an M, I imagine there to be an M. I get an arrow that then highlights or that showcases the direction of the force. Okay? So indeed, if I look at this other mass, then it has a different force. There's a different force. at different locations. That's going to be key. Now, that's one way of looking at it. There's a different force if I imagine I put different m's everywhere. Now, what is the alternative way of looking at this? Okay? And that's why I put an or here. I can also imagine this as the mass, the big mass, m, creating something. This big mass, m, does something, creates something. And I'm going to call this a so-called field, which exists throughout space-time. Throughout t. Now, of course, I know that there's going to be a lot of places where they make this very clear distinction in somewhere in space and then at some time t. I want to prep everyone here for general relativity or even special relativity, where all of this is just combined. So it doesn't matter, right? It's just some point in space and some point in time. But we can imagine the physics behind it. Instead of being forces, right? I put a mass here and then it experiences a force. I can also just say this mass m creates a field throughout space-time. Now, the important thing is that this field exists independent. This is very important. Independent of a test mass. Test mass m. So I don't need this m to even imagine that there's a field that is being created by big M. And that's going to be the key. That's the key difference. Okay? So indeed, we're going to move away from forces, right? So it's different from Newtonian dynamics. That considers focuses, let's say, on forces. And instead, we're going to consider fields. Now, I want to take a little bit of a pause here, and I want to see if if anyone here think of a reason why do we want to talk about fields? Why not, always consider just forces? What's the advantage of considering? I'm just going to give you, let's say, 2 minutes, okay, where you can think. You can just consider, or for those who are quick, just go on Google. But I want you to think about this issue. Like, what is the advantage of considering things in terms of fields rather than forces? I'm going to give you 2 seconds. Okay, I just want to say that I really do appreciate people just typing in the chat, right? Even if you don't speak. when you're thinking about it, feel free to type it. I, have limited capacity to follow everything, but I'll try to go through everything. But I really do encourage it, right? Even if you want to just speak up, I'm completely okay with it. So, but some people are faster typing, or they don't want to, they don't think their voice is good or whatever reason. But yeah, so keep going, and I will try my best to read them. So let's just start at the top, right? Someone says scalar. I don't necessarily know what that entails. Wing Ching, you want to elaborate? What do you mean by scalar? Jeremy. Scalar potentials. Okay, that's one way of thinking about it. I would say it's not the main reason. It's more like a consequence of writing things. But because, and I'll show you that it's not always possible to write a scalar potential. Right? Only certain fields, like fields with certain properties, have a convenient definition of a potential, a scalar potential. And the most notable is, and that's something that we'll see, is when we have, B, the magnetic field, you cannot write that as a scalar potential. You need a vector potential. Easier to add up the effect of multiple sources. Sorry, okay, let me just, there's now a lot of things. I'll go to the top. Can generalize to different dimensions. Someone's saying there's a limit of rate of transmission of information. That's also good. Indeed, so one thing that is much more difficult to consider when you just consider forces is, okay, well, how do these effects propagate in time? Right? Things like waves would be almost impractical, because then I would somehow have to put a test mass and then see how the test mass goes along with something. I have to consider all the dynamics of the test mass and then reconstruct the field backwards. But in essence, it is the field that is moving. And then, if you put a test mass there, then you can get the test mass to move. So that's a good description. Forces seem not to agree with special relativity. Yeah. Actually, I do tend to agree. I think the reason why is a lot deeper. But it is true that for example, special relativity, like Newton's third law, like you've got equal reaction of forces, may not always actually happen even at the same time. If I transform in a different frame, you could actually see this one go, and then maybe sometime later this one goes, and even the direction and things are no longer preserved. They are, but something else is preserved. That's the key. But I agree. Okay, forces seem not to agree with relativity. I appreciate that. I think that's good. Effect of test object is not considered. Right. Now, of course, if you call it a test object, then it's by definition something that does not affect the system. But I think I know what you mean, Chao Ho-in. I really do apologize for butchering everyone's names. But that's true. That's true. Visualization, that's one thing. I do think that's, of course, we don't do physics, we don't study the physics because we can visualize it better, but it is a side effect. So the idea of a field rather than forces is also applicable to other physics realms. Yeah, it's much more generalizable. Fields is something, especially if you work with fields, you can think about other things. You can think about gravity as a field. You can think about electromagnetism as a field. You need to consider problems in whole space rather than one object. I agree with that as well. You don't have to put test masses everywhere. Instead, you just consider the entire field. But describe the strength and direction of gravitational effect of an object. Yeah, that's right. Overall effect. Vector field can be generated. Easier to add up multiple sources. Yep. Can eliminate disadvantage of force action at a distance while having an overview of how the field varies against time. all space. Okay, so all of these suggestions I think are great. So I think that's good, right? These are all kind of advantages and things. I think one major thing that you may not have considered, or at least maybe not that explicit, is actually how a field interacts with another field. Right? How does one field interact with the other field? Like how does the electric field, and as we'll see, the electric field actually simulates a magnetic field, and then stimulates an electric field again, and then a magnetic field. That's a wave, right? And so this effect here, if I just consider in terms of forces, it would be a mess. It would be some electric force. Then how does that then ends up creating maybe a movement of some mass, and then creates a magnetic field, and then. But if I put it in the language of fields, it's much more immediate, much more simple of how a field interacts with another field. Okay, very good discussion. I really appreciate this. So I'd say keep it up, right? I will sometimes just stop the lecture just to give you a question, and feel free to chat, to talk, and so on. And if anything, if you want, keep this same discussion alive on the discussion board. Very philosophical as well. Okay, that's a field in terms of gravity, and that's why we need it. But now we can actually, or at least I want to talk about the different types of fields. Because what is actually a field? Let's consider two fields that we are interested in. In this case, we are interested in either scalar fields versus vector fields. Now, we all should at least have a notion of what a scalar and a vector is. What is a field then? Well, a field is nothing but something physical, okay, some physical quantity that takes different values at different points. In space-time. And again, I say point in space-time. So what I'm saying is it takes different values at different you could say locations and at different times. That's what I mean with a point in space-time. It's a little bit relativity lingo, but it's something that shouldn't be too difficult to understand. Okay, now so that's a very simple definition. That's a field. Okay, it's just some physical quantity that takes different values at different points and different times. Now we can consider one of this physical quantity to be a scalar. Okay, how would that look? And actually, let me try to do this and show you the following. This here, how I'm loving technology. Okay, I'll make this bigger, and I'll make it smaller when I annotate it. So this is our planet. This is Earth. At least hopefully we all remember what the Earth is. I know we've all been locked down, and it seems like the world has basically shrunk to a point. But there is still physical distance. There's still an outside world. Have we all done our geography well? Do we know where Hong Kong is? Okay. More or less. I'd definitely say it's not here. Okay, it's also not here. Somewhere around here. Then okay. Then you've done your geography well. Okay, but let's take a look here. What are we looking at? We see different colors, right? Superimposed into this Earth map, we see different colors. And in this case, it's the annual average temperature. Actually, let me double check whether the video is clear enough. Okay, yeah, you should be able to see it. So this is the annual average temperature. The more red the color, the more warm it is. Okay, and the more blue, the colder it is. You can kind of see, okay, Hong Kong, which is around here, is it tends to be quite a warm place. We can feel it. We go outside, we sweat our balls off. Okay, so but this is an example of a so-called scalar field. We have position somewhere on the map, and then we have a temperature, which is a scalar, right? It's just 30 degrees, 40 degrees. This is an example of just a scalar field. Let me just shrink this now. This here, about half the page. Okay. And so this is indeed an example of a scalar field. Okay. And in particular, there's just a scalar associated to every point. And in this case, our example is the temperature. Okay, now let's take a look at another thing, which is vector field. So again, I'll start with making this big, and I'll make this kind of smaller. Okay, hopefully people can see this. And now what we have is something slightly different. No longer this map where we just have a color on each position. Instead, what we see here, for those who are interested, this is a wind map. This is a map roughly how the currents of the winds go on our planet. And we see basically two things. We see, okay, don't worry about the colors. The color actually means something else. But we see two things. We see narrow, and in this case, even like you can either say the thickness of the arrow or the length of the arrow. But every point here, we have an arrow. Okay, this is just the wind map. How the wind currents go. You can also think about it in terms of a fluid, where the water flow of a fluid. And so every point, we can't just have a single number describing the situation. Instead, at every point, we have two things. Remember, vector has both a magnitude and a direction. So indeed, this is an example of a vector field. Here, there you can take. Okay. Indeed, this is a vector field. And for example, this is just wind or flow. So these are basically the quantities that we are going to consider. Now, if I go back a step, okay, and I go back to this picture, here, gravity, then it should be fairly straightforward to realize what kind of field describes the gravitational direction. No? Are we talking about a scalar field or a vector field? Vector field, vector. Anyone who wants to play devil's advocate and say it's a scalar field? I also don't want everyone to just mimic what the first person says, right? If you disagree and you can tell me a good reason why, let's talk. Anyone opting for a scalar field? I can even tell you that both answers are right. For reasons that I will get to really more next week. Okay? But yes, in principle, it's a vector field. Now, in this case, this is a particular vector field. it has special properties in such a way that I can also use a scalar field to describe this. Okay? But we'll get to the details in a moment. But this is really about whether a field is conservative or not. But in principle, I could write this field as a gradient of a scalar field. Gravitational potential, indeed. So in principle, the gravitational potential is enough to describe gravity. But gravitational potential is a scalar. But how or why is that? Even though, because the outcome is a vector field. That's because the entire vector field is described by the gradient of a scalar field. And we'll see exactly when, what particular instance causes this. And this is also really where the kind of the novelty of this course is we're really going to take a look at these field properties so that we can derive their properties. Okay, so that's it in terms of fields, and so let's just jump all the way to the end now. Okay, I want to first give you the picture of what we're going to try to achieve, right? What are the objectives? And then I'm going to take one step at a time to go towards this. So let's first define the objectives. Okay, what are objectives? And in a way, you can think about this as the objectives for this chapter, but they're also more or less the objectives of the entire course. And that is, very simply put, it's to develop concepts of electromagnetism. Okay, I'm just going to abbreviate this with EM, using fields. Okay. And the way we can do it is we're going to review classic experiments that basically have led to the development of the field concept. But maybe more importantly, we're going to actually look at the mathematical properties. Look at the mathematical properties of electromagnetic fields. Okay. So once we've found the field, we're going to actually study it in terms of mathematics. Like, what does it mean to have a particular field? And I've mentioned already some keywords just now. We've got things like conservative fields. What does it mean to have a conservative field? And what are the consequences of that? And finally, maybe equally important, is we're going to actually also develop the mathematical tools for evaluating electromagnetic fields. So instead of always, focusing on, let's say, point charges and, very maybe nicely, distributed charges, we're actually going to give you more generic tools to do this and how to do it. Now, the reason why this is needed is also because we're going to focus more on fields, and so indeed we're going to be less discussing, kind of some specific property and some specific parts of the volume, but instead we're going to look at the overall the overall properties, like local properties of fields. Okay, so what does this mean concretely? Okay, in terms of what we're trying to concretely get towards is indeed a description of fields in electromagnetism. And especially what we're going to look at is we're going to develop the notion of this electric field, typically denoted by E, and magnetic field, B. Okay? Now these are, of course, assuming that we're talking about vacuum. We use different symbols when we are moving away from them. So we're going to take a look at the electric field and the magnetic field, which are then also properties that we can evaluate at every point in space, x, y, and z, and time. Now, don't worry, right? We're not going to move away fully from Newtonian dynamics. We can always use EM fields to relate back to forces. Okay? This is something, the ability, and again, I can add some time. Right? We always retain the ability to, once we have the fields, to then ultimately ask, okay, but what if I put a test charge or test current here? How is that going to react? We can do all the manipulations, all the field manipulations before that, and then at the end consider, okay, well, what are the consequences? Okay, so that's the first part, right? We're going to study fields, electric and magnetic fields. Now, the way we're going to do that is basically, the fields are specified through, and this is something that you should have been beaten to death with, Maxwell's equations. Okay. And you should have seen both forms of Maxwell's equations. So here I'm just going to go through them both. So this is the integral form, which is basically electric field through some surface S equals 2 epsilon naught, or at least 1 over epsilon naught total charge over some volume. We can also relate the B through some surface, okay, to 0. Remember, these dots are dot products. And then, or we can look at how the field goes when you integrate down some line, and we can see that that is related to the magnetic field, some surface, and the rate of change of that. And here again, we can do the same for B, and that is just a little bit more complicated. It's mu naught, the integral of the current over some surface S plus a time varying part with respect to the electric field. And what we talked about before, when we talk about field-to-field interaction, okay, you can kind of also see an example in the last two equations. Here we have some time, right, some time dependence, but an electric field or a changing magnetic field then causes an electric field. Sorry, 1 second. Okay. The general office calling me. I don't know why. They should know I'm actually teaching right now. Right. Okay. So the bottom two equations, you can see that when one field changes, when a magnetic field changes, you get an electric field. And I know that typically what we've done so far is that we've seen it in terms of experiments. Okay, something changes, like something happens when you change a magnetic field, and then something else moves around, and so on. But here we do it explicitly in terms of fields, just so that we can really consider the physics first. Okay, that's the integral form, and the focus of this course will really be more on the so-called differential form. And in the differential form, we can actually write equations in the following way. We've got the gradient, sorry, the divergence of E, the divergence of B, the curl, or the rotation of E, and we've got the rotation of B. Naught J plus epsilon naught partial E partial T. Okay, so these are the two different sets of Maxwell's equations, and they're completely equivalent to each other. And that's one thing that I will also show, is actually how to go from one thing to another. And in fact, even when we see here, these integrals, these differentials, we'll discuss the mathematical meaning of these in a moment. So don't worry about it if you don't recall exactly what they are, what their meaning is. We are going to go through them. But I just want to show you basically the end form, because it is exactly how we want to say, okay, we want to evaluate the electric field and the magnetic field is through either set of equations, the integral form or the differential form. Now, I want to just take a moment and also, through these two equations, kind of highlight what it is that we mean typically when we look at the integral form. We're considering the field as a whole. If I take a look at the left side, and let me use a different pen. Then here, for example, in this expression over here, then I end up explaining, or I end up calculating the electric field, but over some surface, over some predefined surface. Okay? So I haven't considered the electric field kind of, at different points, but instead I'm just saying, okay, what is the electric field over this entire surface? So it's really a global measure of the electric field. Not global, but kind of like an extended measure of the electric field. But if I take a look at this equation, which is equivalent, then we see something that is not necessarily considering the whole kind of surface or some whole surface, but instead it only looks at the field and what happens if I take a tiny step, right? This is actually a derivative of a field, and I take a tiny step away. And so indeed, the main difference, the difference in kind of the information, not information, the type of information contained is really at that level. Okay? So this is over some volume, over some volume or surface. But here we're really considering some local measurements, some local measures of the field. And that's really, kind of a big difference in terms of, what really you can get out of out of looking at things in the integral form, or looking at it in the differential form. Okay, let's move on. Well, let's take a quick break. Okay, as I said before, I think when we go online teaching, it's best to take a break. But I don't want to just send you off in like a 5-minute break. Instead, I want to, even when you go to the toilet, I want you to be thinking, or at least reactivating your brain, and hopefully to physics, not something else. So let me just give you some very simple thing to think about, and just to prime our discussion next. So if I have some charge 1 and if I have some charge 2, okay, very simple. Q, the question is just, is the force attractive or repulsive? Okay? Or if you will, when is force attractive or repulsive? Okay, let's take a 5-minute break. It's 3:28 according to my clock now, so let's gather again at 3:33. Okay. Guys in a bit. Okay, welcome back, everyone. This was kind of a freebie, a very simple question. Anyone want to take a stab at this? Feel free to type it in the chat or, well, just shout the answer. When is the force attractive or repulsive to charges? Let's go. Like charges repel, unlike charges attract. Okay, that seems like a good answer. Anyone disagrees? I want to play, go super hardball and say, I disagree. Okay, more or less, more or less. Anyone have thought about more special situations? What if I make one charge moving? What if I end up accelerating one charge? Okay, anyway, food for thought. Food for thought. Okay, let's move on. Okay, so the first experiment I wanted to explain is something that you should have all seen, maybe even in high school already. So I won't spend too much time on this, but I do want to stress that this really is the foundation. This is the beginning of kind of maybe modern electromagnetism, or even just electromagnetism altogether. So that is Coulomb's experiment. Coulomb's experiment. Now, oftentimes what you then end up getting explained is that, oh, Coulomb did some experiment to measure the charge, the force on two charges. And then it says, oh, okay, it's blah blah blah. Does anyone actually know how the actual experiment was conducted? How would you measure the force? Let's say even if I was able to put two charges here, how am I going to measure the force? I'll give you a minute or two to think about it. Feel free to type it in the chat box. Use a torsion balance, spring balance. Okay, yeah, I see ideas coming up. Because indeed, right, it is not, you can use gravity, yes. In principle, you could even use gravity. So the concept is actually, is simple in a sense, right? We need, how do we measure forces to start off with? And so we need something that kind of pushes back. And I see a couple of ideas here, torsion balance, spring balance, and gravity. So yes, those are all perfectly legitimate ways. The only prerequisite is that it's a system that I've then calibrated, right? Even if I do a torsion balance or spring balance, I should be able to have calibrated it so that I know, okay, what is roughly the amount of what is the force? This could be calibration in different things. So let's consider the first idea here. It would be a torsion balance, right? And I can proceed doing something like this, where I have a force, sorry, a charge here. Oops. I have a charge here. No, okay. I have a charge here, and let's say I have a charge here. Okay, I have two charges here. Let's call this Q1, and this is Q2. And indeed, okay, let me make things a little bit easier to do one, and let's spread this out a little. And indeed, if I'm curious about how much force there is on Q2, I could link this up in a torsion balance, and I could just have this and suspend it like this, and I could see, okay, well, how much is this thing going to be rotated, right? If this is some something that allows you to twist. And indeed, then by looking at the displacement and knowing what material this pivot is made of, I'm able to do the measurement. And indeed, the original experiment, Coulomb's experiment, is based on this. But I could have equally I could have equally done something indeed like 2, 1, some 2, connected here to some spring, and then indeed look at this displacement over here. Okay. Now, of course, there's maybe slightly difficult because how do you keep everything balanced? But it's not undoable. And maybe even in the most extreme case, right? So this is a torsion spring. I could even indeed try to balance gravity and electromagnetism. Okay. I could have, here's the Earth, and I could have an object with some Q and some mass. I'm going to say, okay, well, I'm going to have another Q2 here with some mass as well, mass 2, mass 1, and I'm going to see, okay, well, how can I keep this system balanced? But if I know what this is, what the what the gravitational force of the Earth is, I should be able to measure something. Okay. Now, of course, this is a little bit more complicated because we're dealing with two different fields. We're dealing with the gravitational field and the electromagnetic field, which is could be more complex. You need to know what M1, M2s are, and so on. But these are all possible. Okay, so indeed, Coulomb's experiment, and basically the outcome is something that I think we all know. So indeed, the force between Q1 and Q2, Q1 and Q2, and Q2, okay, is proportional to Q1 times Q2 and inversely proportional to the distance between the two. So if I call this distance here R, let's see, R12, then it's inversely proportional to the modulus of R12 squared. And so if you put this together, you can actually formulate so-called Coulomb's law. So we can write Coulomb's law simply as the force between 1 and 2 is some constant, which you don't have to care about yet, times Q1, Q2, and indeed I can do this as R2 minus R1 squared, R2 minus R1 divided by R2 minus R1 and the modulus. Okay? Where here, this one is just the R12 unit vector. So we got indeed what we needed, right? It's proportional to Q1 times Q2, and it's inversely proportional to the distance between R2 and R1. Now, for those who are following Griffiths, the book, they have this curly R that they use for R2 minus R1. You can also write R12, whatever you want to do, or you just make it even explicit and say it's R2 minus R1. I'm very okay with either. Okay? And indeed, if we look at this law, we can indeed identify that if F12 is bigger than 0, then the force is repulsive, right? Because this is the force between 1 and 2. If it's bigger than 0, because we're giving the direction is also 1 to 2, then the force is repulsive. And so that only happens with Q1, Q2 is bigger than 0. Indeed, if they're both pluses or if they're both minuses, negatives, then the force is repulsive. And here we've got F12 is smaller than 0, which means the force is attractive. In this case, it's Q1, Q2 smaller than 0. Of course, this is under the assumption that K, the constant, is a positive constant, but it's a constant we can define basically ourselves, whether it's positive or negative. It's just how we want to define, attractive or repulsive. Okay, so this is Coulomb's law, and this is something that I hope we've all seen. If you've done 2041, you should have seen Coulomb's law. Now, of course, for us, that's not the end story, and it's something that we want to look at more specifically, or actually, we want to rewrite it. But before I do so, let me just quickly make a very quick slide, because this is something that I expect everyone to have seen before, but in terms of units. So the actual value of KE depends on units. So indeed, depending on how I choose to represent my charges, this constant changes so that ultimately it becomes a force that we typically measure in newtons. So in the SI system, actually, do people know what SI stands for? It's French. Yeah, it's standard international. Yeah, so it's the yeah, the National de Unités. Okay, for those who are interested, I really hate French acronyms. The order is completely the reverse. Like system international. Why not international system? Why not IS? But maybe nowadays it becomes a little bit more difficult to change it back into the IS system. But the same with football and stuff, right? FIFA and things, all French acronyms, and it's all it's all the wrong way around. But we'll have to deal with that French people feel that their language is important. Okay, so indeed, in the SI system, the constant is simply some number, and this is just experimentally verified, and m squared c minus 1, where indeed c here, where yeah, this is just so-called Coulomb, named after Coulomb himself. C is the unit of charge. Okay. Now, this is all something that you ought to be familiar with. I mentioned this mostly for completeness. I don't expect you to ever have to really punch in numbers to come up with some exact number, like so and so many newton. I don't typically think that's very useful. That you may have done that in 2041, but here we're focusing on fields and things. Um, whether you can use a calculator, I don't find very important. Okay, so the only caveat is, of course, this constant is typically, or alternatively, uh, you can rewrite this KE as, in particular, you can do it as KE equals 1 over 4 pi epsilon naught. In this case, epsilon naught is 1 over 36 pi times 10 to the 9, 1 over Newton over m squared c squared, which is basically just so-called the permittivity of space. Okay, and if I put all of this together, I get that the force 1, 2 is just 1 over 4 pi epsilon naught, and then the Q1, Q2, R12 squared, and then R hat 12, where, just so you know, I don't know whether I've made it explicit last time, but hat okay, so that's just the regular vector divided by the magnitude itself. Okay, now before I go completely I go where I want to go, I just want to also bring up the so-called principle of superposition. There's the principle of superposition. So we've so far only considered point charges. And that's all well and fine, but as I said, this time around we want to move a little bit to more complex stuff. So instead of just considering point charges, we also want to have distributions of charges. And so we have to actually consider a whole bunch. Now, the first subtlety I want to highlight is what is actually a point charge. Okay? And the notion of a point charge is actually rather subtle, because when I talk about point charges in this lecture course, when I talk about point charge, I do not mean protons and electrons. You want to know why? I'll give you 2 minutes. Why, when I talk about point charges in this lecture course, do I not mean, almost explicitly, I do not mean individual protons and electrons. Finite size, protons and electrons still have size, too massive, negligible charge, proton and electron has size. Okay, so I see that there's some theme coming up with in terms of size, and I actually want to ask people, what's the size of an electron? Someone, I understand proton, yes, you can give it a size. What's the size of an electron? Actually, those who say protons and electrons still have size. Need a number. 42, 38. I mean, okay. The other aspect, I'll get to the size and thing. The other aspect is mass, right? So point charge does not have a so-called mass. That's also a little bit, I'd say, tricky, because, well, we're not considering gravity here. So whether it has a mass is not that important, even though I know what you're trying to say, right? Because whether something has a mass or is massless um, does make a difference. But in this case, it's not too relevant because we're not considering the gravitational interaction. And even then, a point mass could still have a mass. I could say, even when I considered this this slide over here, no, this slide over here, right? In essence, these are point masses. So, yeah, they could still have a mass, two masses. Oh, okay. So it has a little bit to do with size, but not exactly for the reasons that you think. And I'll just, I'll try to discuss the answer with you, because as you'll learn in this, I expect most of you are also taking quantum mechanics 1 this semester, this term. Is that still Höbami? No? Who's teaching QM? Okay. Oh, that's unfortunate. Not because of the other guy, but I really like Höbami's teaching. I think he's an excellent teacher. He does everything very thoroughly, very much, with learning in mind. I really think he's a good teacher. I think, you know, getting your first lecture course on quantum mechanics from Höbing is I think is a treat. Okay, so Zhong Ji, I don't know how to pronounce this. It says uncertainty, and that is exactly the point. Okay? So when I talk about a point mass or a point charge, it's something that I could pinpoint, I could locate, I could associate an X, Y, and Z to it. Okay? So for example, I should be able to write, okay, well, what is the exact location, right, of this Q in terms of, say, X, Y, and T, X, Y, and Z. But as you'll see in quantum mechanics, there's Heisenberg's uncertainty principle. I can't have something, you know, if I could localize it to a single point, then the momentum is undefined. And vice versa, right? If I could pinpoint its velocity, then I can't pinpoint its location. There is this uncertainty. And so, indeed, when I talk about a point charge, you know, I do not mean kind of electrons and protons, because those are quantum mechanical concepts. So indeed, you know, we need quantum mechanics. Localization of particles. Now, this course, I'll try to, you know, I'll try to stay away from quantum mechanics as much as possible. But as we'll see as we go along, it's not always entirely possible. It actually turns out that quantum mechanics and electromagnetism are, at some point, they're going to be related to each other. And for those who are, you know, extra curious, this will ultimately culminate into something called quantum electrodynamics, okay? Where, you know, also the concept of quantum mechanics will come in. And when we consider materials, realistic materials, quantum effects are actually important. And so, you know, one way or another, somehow we need to get there. Okay. So instead, what do I mean with a point charge? Okay. Point charge. This course is simply a, you know, you can say it's an infinitesimal, you call it sphere or some volume of charged material. The material is charged, and I'm just going to take some infinitesimal sphere or you know, or some volume of some charged material. That's because I do need to be able to consider its location and everything. Okay, but now when we want to consider a charge distribution, I need to actually do something else, right? I can no longer, you know, I can no longer simply take Coulomb's law and say, okay, well, what is the force if I have a charge distribution? And in order to do that, be able to leap from, let's say, a single charge to, you know, a charge distribution, I actually need to do, I need to make an ansatz. Okay? So it is actually an ansatz. If I say that, you know, ansatz is so-called principle of superposition. Okay? Which basically states that the interaction of any single charge with another charge is independent of all other charges. Okay, so that's the principle of superposition. It basically says that if I take, you know, if I have this volume of charge and I just take that one little point charge out of that, then some other point charge here, then I can ignore all the other charges if I just considered, what is the effect of this point charge on that point charge. But it also means that then I can add up all of the ones, individual ones, to make up the charge distribution. So that's the principle of superposition. Now, I want to give you another question. That's the question, why can we use superposition? So why, in reality, when we actually think about, when we actually do, all of our electromagnetism, why can we use this ansatz of superposition? Give me 2 minutes, or think about it. Type whatever you have in the chat box, shout, whatever. But think about it. Why can we use this ansatz? Any other thoughts? Okay. So far I have 2 answers. One says the ansatz is supported by experimental results. And one says vector addition preserves linearity. I want to go to the second one first. There's this notion of vector addition preserving linearity. The question is more, why does the presence of the other charges not alter this charge, the interaction of this charge with the outside one? Right? And so you need the ansatz of superposition before you can actually vector add things. Jason says the effect cancels out. That's a consequence. It's not the reason why. Okay? Because even when you say canceling out, you need to then, how do you add the contributions or to even cancel out? You need to have already defined a rule how you can add all of these things together. And that's why it's an ansatz. Third law, Maxwell's equation is linear. I mean, the answer is basically is actually what Anson said. So even why is Maxwell's equation linear? Is because we have the principle of superposition. And this separates physics from math. Right? We're physicists, we study physics. Or at least most of us study physics, sorry. There may be students from other departments here. But this is a physics course. Very simple. It comes out of the experiments. Right? That is the only thing that makes, in terms of physics, that makes something law, or more just kind of like a mathematical curiosity? So whatever I do, whatever you'll see me do in terms of maths and things, I derive here, derive that. In the end, it has to be experimentally verified. It has to be that way because of experiment. And the principle of superposition is one of these things where we can start with the ansatz, and I can then write down the whole theory, including Maxwell's equations and everything. But if I measure it, or if I use Maxwell's equation to calculate something, and nature tells me something else, and that's nature, right? So it's a little bit of a kind of a point I wanted to make specifically, is there's nothing kind of deep philosophical about it necessarily. I mean, you could go all the way to the anthropic principle and say, okay, well, if this ansatz wasn't correct, then no humans would exist, and therefore, by the fact that humans exist, this ansatz must have been correct. That's the basically the human-centric way of thinking about it. Which I think is circular, but string theorists love this stuff. No, but it is just the experiment shows that that is the way nature works. And therefore, Maxwell's equation flows out. Okay? So I just wanted to kind of impress upon you, that we are, despite all the maths that we're going to do, we are still physicists. Right? It all comes from the experiments. That's why even in my derivation, everything, you start with Coulomb's law. That's what actually is experimentally measured, and then we write down the physics and the maths that basically describes exactly that. Okay, so let's move on then. So now we have the principle of superposition, and so we can now write charge distributions. Very simply, right? Charge distributions. Okay. And so we can generalize Coulomb's law. Using superposition. So if we have a collection of charges, okay, so let's see here, we have just a collection of charges spreading out everywhere. We have Qj, and they're in at some position Rj, and then we have our, oh dear, we have our test charge, okay, Qi at Ri, Ri. Then because superposition tells us that the interaction of this Qi here with this element here is independent of all the other elements. So indeed, whatever force there is, maybe this direction, then the one from here would be then in this direction, and so on and so on. Okay? So I can simply write now Fi equals to Qi over 4 pi epsilon naught, the sum of j for all the j's in, if this is v, just call it v for j in v, we have Qj divided by Rij squared and R hat ij. Now I can also make this for continuous distributions. Then instead of all these discrete elements, I basically have that the charge element is either a density times some volume, or some surface density times some surface, or even some lambda times some line element. And And then indeed I can then simply write that it is some integral, right? FQ is indeed Q over 4 pi epsilon naught, and then I can just do an integral over small q here, dq, and this is then r, let's call it r minus r prime squared, r minus r prime over r minus r prime, like this. Okay, where the r prime is whatever coordinate is inside my distribution, and r is the location of q. In this case here, if you expand this dq, you can do an integral over the volume. If you have just over a surface, then this dq is just some sigma, and then over some surface. Okay, so we basically are now landing at the last state, basically. That is indeed the electric field. The electric field. Now, why do we need this notion of a field? Well, if I simply, again, consider the Newtonian experiment, then what happens? Well, if I remove test charge, then no more force. Okay. If I have, indeed, I have some big Q and some small q, but if I remove this, charge, then there's no more force. And then you can say, okay, well, okay, nothing happens. There's nothing there anymore. Because the only way which I know something is there is when something happens. Now, the alternative way, and that's more the field theory thinking, is, and that's what I read, or say space is affected by charge distribution. Okay? So regardless whether there's a test particle there, my initial charge distribution, let's call it big Q here, already alters space. The properties of space have been changed by the inclusion of this charge distribution. And then what I can do is, well, how do I get this change? How do I consider this change? Well, one thing I can do is I could still consider the force, but I make Q going to 0. Right? My test charge, I go smaller and smaller, smaller, right? Whatever charge I'm. That's almost the definition of a test charge, is that in the limit that Q goes to 0, is there still a force left? Well, this is exactly what we define to be electric field. Electric field is at the limit of Q goes to 0 of 1 over Q FQ. So it's the force per unit charge in the test charge limit. Now, I can make different distinctions now. So if it's a discrete distribution, then E of R is simply constant sum of Q case, and this is R minus Rj cubed R minus Rj. Okay, so it's basically just dividing out the initial Q if we look at in terms of the forces. Okay, I just get rid of this Qi. Okay, now for continuous distributions, I basically have the following. I can have AE integrating over a some small dq, and indeed then just R minus R prime cubed, sorry, minus 3, and then R minus R prime. Okay, so I'm just integrating over all these small elements, Q. Again, remember, if I talk about a surface, then it's just subsurface density times some surface element. If I'm talking about some volume, it's just some volume, some volume density, some charge density, integrated over some volume. So this is basically starting from Coulomb's experiment. We arrive at this electric field, right, where we're interested in just removing the influence of the test charge. Okay. So next time, because we're running out of time, next time what we're going to do is we're going to take a look at assuming, well, having arrived at this electric field, what are the properties of this electric field? Like, I can write the electric field this way. What does that mean in terms of properties? And so we're going to do, basically, we're going to do a few things. We're going to start with a so-called Helmholtz theorem, which basically says, what do I need to do to fully identify or fully consider a vector field? And that's Helmholtz theory. And then we're going to take a look at various differential operators that we can that we need in order to quantify the electric field. But before that, next time I will also introduce the magnetic field, and then we're going to do Helmholtz theory, Helmholtz theorem, and the different differential operators. We're going to take a look at that in order to fully quantify and specify vector fields. Okay, that's pretty much it for now, for today. Two things I want to end with before you all leave. Number one, fill in the survey of how you want to best do the exercise classes. It's on the blackboard. Just go to the course outline, and you'll see at the top, you'll see the survey. Please do fill it in. Okay. If you don't, I'm just going to make an educated guess of what you want, unless you tell me what it is that you want. Two is actually something that I hope you will do. Well, I expect you to do, and that is when you log in to Zoom, please use your full name. Okay. It's something that I hadn't thought about last time, but I do think that in terms of safety and privacy, I think it would be good for us to be able to identify whether you're a student here or not. Okay, so please do use your full name. I see things like dots and just just the first name and so on. I do hope that I do expect almost that you use your full name so that we can also identify who you are. Okay, right? You can identify who I am, and I hope that at least you put your full name out there so that I can identify who you are. Okay, those are the two administrative things I wanted to leave with. Let me open up the floor for questions and comments. If you want to stay around for that, that's fine. Otherwise, you're free to go as well. Okay, see you guys next week. I don't see any questions or things, in which case I'm gonna stop the recording and I'm gonna close out the meeting. Bye bye, everyone.
Bye.